Good morning, children. So, I am here again with you with something new. Can you recognize the image of this person? I think you can. Yes. It is no he is no other than Albert Einstein. Okay? So, we are going to start the fourth chapter of Beehive, a truly beautiful mind. Right, till now we have read about the two more great personalities. They are Alvin Glennie and Bismillah Khan. So now we are going to read about Albert Einstein. Fine. So let me tell you the introduction of the chapter. Seeds of success are sown early in life holds true for most of the people who made it big. So it is believed that the seeds of success are sown early in the life, in the childhood. Okay, but the story of Albert Einstein is something different. But the story of Albert Einstein refutes all such claims because he was not an extraordinary boy in his childhood, but in spite of this, he was considered as abnormal. So that's why this claim, Albert Einstein's life, refutes all such claims. The chapter presents the life story of one of the greatest scientists of the world, Albert Einstein. His work on light, motion of particles, electrodynamics of moving bodies, and energy was outstanding. So we all know that he was a great scientist and what he has given to world. The story shows Einstein as a human being, a fairly ordinary person who had his likes and dislikes, his streaks of rebellion, and his problems. He says that he was as ordinary as we are. He has struggled a lot in his life. He had his own likes and dislikes, okay, and how he was in rebellion and what were his problems. So, that we are going to read in the chapter. It highlights the qualities which makes person genius and great, but he had certain qualities which has made him great and genius. So we all know that what he has given us, okay, his achievements. He has told that time is relative while light is constant. Fine. And one more thing he has given to world. Albert Einstein's first achievement is making the first atomic bomb. In 1905, he created the atomic bomb. He released a small amount of matter. It was E is equal to mc square. So in this chapter also, we are going to read not about his childhood, but about his achievement also. So here E stands for energy, M stands for mass, and C stands for the speed of light in a vacuum. And we all know that one of the famous thing which he has given to world is spatial theory of relativity. Okay, according to which time and distance are not absolute. So to understand more about E is equal to mc square, okay, I am going to share a link with you to understand the spatial theory of relativity. So you must watch that video to understand it in a very perfect way. Fine, children. So what happened? He was led to make the atomic bomb by President Franklin Roosevelt, the president, signed the letter known as the permission to make it. So he has written a letter to the president to make bomb, and the president had just signed it. From my words, I guessed he make it to end the war. Fine. So afterwards, what happened? How that atomic bomb was used? That we are going to read that how Americans had just used an atomic bomb as a secret project, and how they have dropped it on the Japanese cities of Hiroshima and Nagasaki, and how it pained Einstein a lot, okay, and how he formed a campaign for peace and democracy. That all thing we are going to read in this chapter. So before this, you must watch a link which I am sharing with you on special theory of relativity. Okay, children? Thank you.
Time. You can't see it, you can't hear it, you can't weigh it, but we experience it every moment. The whole piece of time is a landscape, and we move through it, slice by slice. But do we really understand time? Is time same for everyone? To understand time, let's go back in time and make a small journey with a certain young patent clerk, Albert Einstein. Imagine you're traveling with Einstein in a train moving at a certain uniform speed. The train, relative to the outside environment, is in motion. The two of you sitting inside, on the other hand, observe each other as stationary objects, as both you and the train are moving at the same speed. Hence, relative to the train, you are stationary, and the laws of physics stay same inside the train as they would on the ground when you are standing still. Now let's consider you get off the train and observe it moving across in front of you. Now you are stationary, and relative to you, Einstein is moving with the same speed as the train. This is the phenomenon of relative motion, and we observe it every day. Does everything in the universe observe this relative motion the same way? Yes, everything except light. Light behaves in a different way. Imagine you have a light clock with you. This light clock has two mirrors in the opposite directions and a light beam bouncing between them. Now, let's say the distance between the two mirrors is d, and the time for the light to cover that distance is t. For the sake of simplicity, let's say it's 1 second. So, when this clock is with you at rest position, the light bounces between the mirrors, covering distance d in 1 second, which gives us the speed of light s. Now remember, speed is distance per unit time. Now consider Einstein also possesses the same light clock with him. Only this time, he's traveling in a spaceship along with the clock. When Einstein travels in a certain speed, the clock travels with the same speed of the spaceship in the same direction. Here, light has to travel an extra distance in the same 1 second. Let's consider this distance to be capital D and represent the speed of light here as capital S, which has to be greater than small s. But something's wrong here. Because in the late 1800s, the Michelson-Morley experiment tried to detect the relative motion of the matter through an ether and concluded that the speed of light is constant. This cosmic speed limit is known as c. So in our little scenario, small s and capital S are equal. So, for the speed of light for both you and Einstein to remain constant, something has to give way. That something is time. It turns out, time slows down when you travel faster and faster, nearing the speed of light. So, the faster Einstein travels, slower the time passes for him. Hence, what could be a day for Einstein in space could be as much as 50 years for you on the ground. This became the fundamental conclusion of the theory of relativity, a theory proposed by Albert Einstein in 1905. This theory broke the traditional understanding of time as a constant entity and proved that time, in fact, is different for different observers. The theory of relativity led to many other invaluable findings, the most famous of which is the equation E = mc². But more on that later.